So for this final lecture, I will try to make it 2 lectures, but we'll see if I can make it. So in the first part here, I will talk a little bit about user interface concept for exploring forms and structures. And it goes into how you can look at finite element applications user interface design a bit differently than what has been shown before. So computational tools and architecture engineering. So this is the typical simulation cycle in many applications in finite elements and the finite element method. You define a geometry, you add your forces and boundary conditions, define materials, you run the simulation, and then you evaluate the results. And then you iterate over and over like this. Some of these steps can be quite long, which prevents you from actually interactively working with the model. So this is an example here from an application called Hakon, which is software for simulating hardening concrete. So in this case here, this is the geometry. You can also see the mesh. You define the materials. You define the boundary condition. In this case, it's 10 degrees outside. And then you do your calculation. You wait until the simulation has been completed, and then you get the results. But what if I want to, and then if I change the model again, I have to go back from the beginning, change the geometry, do the time stepping again, and then look at the results. So there is one problem with this aspect is that you don't have a feedback between the modeling and the visualization steps. And there are also discrete computation steps that interfere with the design process. And also, if you are discussing with a client or a customer a design, it's kind of hard to sit and wait until the calculation is done and then go back again. And it's difficult to understand the behavior of the structure. There are some reasons for this. That could be that the computation can take a long time. That prevents you from doing this interactive. But we have quite powerful computers today. So a solution could be we remove this discrete computational step. So when we do a change, it is automatically calculated on the right side. So you have a kind of result window available all the time. When you change the model, it calculates in the background, presents the results. Instant feedback, you also get a better understanding what happens if I change a parameter in the model in some way. It also encourages you to explore. I mean, what happened if I change something here? Could I change the material? And you immediately get the result back. So how can we achieve this? So this is very short computer theory part. So a computer usually has a memory, and it also has a CPU, a central processing unit, that actually executes your program one task at a time. So in this case, we have what is called one CPU core, and it can execute one task per processor at the same time. So having a computational code here, it has to first work with the user interface, run the calculation. It has to wait for it to complete, and then display the results. So one task. Today we have computers with multiple CPUs or cores. So in this case, this is a quad core or a processor with 4 cores. And this processor can actually do 4 tasks simultaneously. And many computers before could do many tasks at the same time, but in Windows, if you have one core, you slice up the time between the tasks. So if you have a single processor, can only do, it takes 4 times as long. In this case, you have actually 4 processing cores that can execute tasks in parallel, and that can speed up things. So if you look at the modeling task in classical computation, you have the modeling, computation, visualization. So we can try to do things. So let's do modeling at the same time as the computation. And we can do the visualization at the same time. We can divide them up into different cores. So we can have the modeling driving the user interface. We have the visualization as a separate task and the computation going on at the same time. And you can have multiple computations as well, so you can divide up the actual computation in multiple tasks. So solving a equation system with NumPy, we'll use that in this course. NumPy can actually take advantage of multiple cores of your computer to actually execute the solving of the equation system faster. And if we look at technology trends as well today, we have clock frequencies hasn't increased a lot over the last years. It has kind of stopped at 3 to 4 gigahertz. But what has happened is that the cores of the CPUs are increasing. So today it's not common to have 12, 24, 48 cores, even 64 cores in a single processor. That means it can actually execute 24 up to 64 tasks at the same time. And also, if you look at your graphics cards, they have like 500 to even 4,000 cores per accelerator. And these cores are not the same as you have in the normal processor in your computer. They are specialized cores, but they can actually do a lot of things really fast. That means that you have multiple teraflop. Flop is floating point operation per second performance on a normal workstation hardware, and 200 to 400 giga floating point operations per second on mobile. So we have a lot of power in our computers. However, many of these computational tools actually doesn't take advantage of this. They kind of use a single core, we wait for the results, we present the results. So many complex finite element type simulation can actually be achieved in real time. I've actually seen some finite element codes that was restricted by using single core, and also be restricted by writing to disk all the time. And if you remove those things, many of these complex can be done in real time. And also you can have multiple, you can have, if you have a model that is, you can have an application look at, is it stable to calculate? If so, it does a calculation all the time in the background. So behind the scenes, it actually calculates results. What you can do with this is that you can actually manipulate models directly with computational feedback, which enables you to explore the models in completely different ways as before. So also look here. So this is one thing that has been coming in the company in the late 5 to 10 years is touch panels and iPads that makes you interact with the model directly. So by pointing the finger, you can actually modify the model in real time on the screen. And that has enabled us to do a lot of things. So, and also these user interfaces involve direct manipulation of the objects. And that methodology to use interfaces that users get the impression of actually moving things on the screen by pushing the finger and moving the node. It will move on the screen as well. Mouse-based interactions, there is a layer between that's mouse and the computer. But you can adapt this. You can add touch to existing applications as well. So in this direct manipulation, you have this model geometry, you simulate or visualize. You have this loop all the time. Instead of having this outer loop, you simulate or visualize if it's possible to do that. Otherwise, you don't display the results. And you do that all the time. And then you can directly see the effects of changing things on the screen. Yeah. So this is also, you have the simulation all the time if it's possible to do that. So this is an example of this. This is from the force-fed application where we move the force and the results are computed in real time. And you can also move the mouse like this to move the force, and you can see the stress field changing immediately. That just gives you another dimension of the user interface. Directly models, direct conceptual modeling, explore user interfaces, and also touch removes the need for special input devices. You can point directly and move it. It kind of gives you a direct connection to your model. And it also, if you have a large touch panel on the table, you can actually have multiple people interacting with the model at the same time, like big surface panels that you can also provide. ForcePad is one of the applications I want to show that has been modeled this way. So this is the application, what it looks like. You have left here, you have different modes, and you have, this is the result part here. But the things with ForcePad, it uses paint program metaphor instead of geometric modeling. So you actually paint the structure, just like you do in Photoshop or in Paint.net or GIMP. So ForcePad is a finite software for conceptual design and teaching. So it focuses on teaching, but providing speed, interactivity, and use. In engineering, you have an action and precision, which is something that you don't need in conceptual design. But it's, in later steps, it could be nice to go in deep, but that is not the focus of ForcePad. It's a two-dimensional finite element application, and it uses the concept of an imaging editor. So in this case here, you can have this iterative design process. You do some sketch, refine, and then you accept. This is the iterative process. Yeah, I can skip it because it's something I discuss here. So this is the normal way of modeling a flat. So you define the geometry, which is you're doing in this course as well, and you create a element discretization from the geometric model. ForcePad is a bit different. So in this case here, you draw with your pencil or your pen with pixels. You add constraints and forces, and then the element mesh is created from the pixels. So in this case, this is a coarse mesh. You see it's kind of very wide, but it also uses, if some of the pixels are also, it kind of uses gradient or grayscale here to how much difference there is in certain parts. So this is the element mesh here, and this is the method here. It kind of calculates how much of the pixels inside this element here, and then it averages the stiffness here, depending on how much is covered on the element. ForcePad also has an optimization mode. So if you have a model you draw like this, it can actually calculate the optimal shape depending on that load case. And you can also set the constraints how much material it should use. In this case, I say I want to have 30% material, and it generates a model that contains 30% material from the original model. And this is the way you have 3 modes. Sketch mode, where you draw, physics mode, where you add the constraints and forces, and action mode, where you actually do the simulation. And then we have a 4th mode that is outside here for optimization. And ForcePad have been used in many courses here. So this is a material shape and force course that we had a couple of years ago, where they looked at bicycles and tried to optimize the shape of a bicycle. Also, KTH has been used in a construction course to study the flow of forces and stability, and they did real models, and they did a qualitative study in ForcePad to see where the flows of the forces were in the structure, and also the deformation of the structure. So let's see if we can do a short demo of that.
Den kanske går inte längre.
Nej, men det används en annan kurs med annat namn nu. So there's a different course that uses. So this is the ForcePad here. So you can, if you want, you can do a draw like this. And then you can do apply constraints like this. So then we are done. You can go into the action mode like this, and then it calculates the principal stresses here. So in this case, it's red is tension stress, and then compression is blue. And you can also look at deflections like this, stresses inside, and you can also change the rotation of the force like this to see how it affects the stress field or the principal stresses like this. And if you go back here and I do just try to see, we can do an optimization problem like this. Just draw a triangle, put some constraints here. And then we add dead load. So this is a eigenvalue or dead load. And then we do calculation like this. So you see a stress field here. And we can actually make it more visible like this. You can see here that you get tensile stress here, and you get this kind of arch shape here. But then we can do optimization here. So we do this one here. You get these artifacts here that is tries to optimize the shape and redistribute, and sometimes you get it. But you can see that you get this arch here. And if we stop the calculation here, it's a bit. It should have been perfect versus here, but you get this kind of iterate. But you can change the ratio of material as well, and then you get a thicker structure as well. So that was force pad.
But from that, can you assume it should be an arch, or do you have to have all those other things in the structure?
No, it can generate. So you can set the ratio how much material you should save. And I put a bit too little, so it removed too much now. But if you have it's constrained in both directions like this, you will get an optimal arch shape because it's a dead load weight, and then you get the optimal.
But we get these boards or something.
Yeah.
You have to include them, or could you exclude them?
You can. What you can do is you can go back again, and you can erase them with an eraser, and then you can go back again and do another calculation, and then you get better. Okay. But I think I made it too thin, and also the resolution of the elements are a bit too coarse. So it's a bit, you have to tweak it a bit to get it correct.
So you know which shape it had to go to, and then you erase the bits you don't have to be there.
Yeah.
I know.
So you can go back and forth between the modeling and also the optimization. And if you put a block and you put loads on top, you can get this arch with actually supporting the loads on top. So it builds up supports automatically.
Yeah.
Yeah. Another example I want to show is objective frame, which is an application I did for my PhD thesis a long time ago. And I have updated this application now to be even more real time than it has been before. So this is how it looks. So it's a 3D beam truss analysis tool. It has been a test bed for developing new interface concept for 3D development applications, implemented in C++, OpenGL, the Eigen matrix library, which is a really powerful matrix library, almost like MATLAB, but in C++. And then something called ImGUI, which is an immediate mode user interface, which I will show you just in a second here. So what we can do with this, you can do real-time interaction with models, and you can see direct feedback when you're modeling. You can animate. The computations are done in the background. There are also plugins for generating geometry, and you can export the model to call from the Python as well. And then we also had another PhD down in Locason who added user interface here with a special input device here that can get to your fingers. So you can actually model. You can manipulate the model using your fingers. So you have some tweezers here, which you can move the model around. This was kind of before we had VR. So today you can have fingers in VR to do it, but haven't ported that to VR yet. So this is the object frame application. Looks like this. A workspace like this. Now I will do. You can model here by placing nodes like this, and you can scale the resolution a bit. And then you can do one like this as well. So you just click on two nodes and we create a beam. Like this. But what you can do with this as well, you can do, for example, you can do actually do. So you have a parameter here. You can set. This is a truss. You can quickly create a structure like this. I can create. So you can set constraints like this. Now I'll do a pre-model here because otherwise I don't finish in time. So let's see here. So I have a model frame here like this. I'll zoom in a bit. It's a bit hard modeling without the mouse here. And I can place a load here on this one here. So I can, for example, like this. So I can actually try out and see how the structure interacts. I can also see where the most affected beams are, like this. Here I can see the moments as well. And you can do this on larger structures as well. It should have. Okay. Sometimes it doesn't work. Okay, but you can also, if you add a lot of load cases, you can actually change the scaling of a load case here and manipulate it in different ways. So let's see if I can just. My computer is not optimal for this, so that's why I can't use it. But this is the idea. So you can modify and work with structures in real time. Then we also had an application called Sketcher Frame. Unfortunately, it's not in the App Store anymore, but hopefully I can make it to the App Store again. And this was a study on how to use finite element applications on an iPad. So try to create an interactive conceptual tool for education, communication, discussion. using an iPad. So the idea was kind of have a setting where you can do simple 2D sketches and have it calculate all the time to see the effects when you change different aspects of the structure. So it uses a direct manipulation interface, 2D frame truss analysis code, no simulation button. There's a continuous simulation cycle. It automatically detects mechanism of structure, and it only simulates when the structure is stable. By default, you have hinged beams, but you can add rotational constraints to your structure as well. Yeah, it's the same thing here, but I can show you here how it looks. So basically here, you don't see the finger here, but basically it's worn with the fingers like this, and it automatically adds nodes to the structure. So this is how we model like this. And then you just kind of roll with your fingers like this to create those bars.
Is there a scale?
Right?
Is there a scale?
No, and it's more qualitative, so it's not you can't set the scale. And the idea is not to display a lot of results, just kind of see what effects it has. You see, you just put the finger here, so I press the finger on this here, and you can rotate it around. You can see the structure. And here you can see the stresses or the forces in the structure in the beams. And you can have two more loads. Okay, now he actually changed the nodes here to be fully fixed, so it's they're fully connected, rotational as well. And you can see the displacement of the structure. So that was give you some interaction to kind of think out the box when it comes to user interfaces. It's possible today to do user interfaces where something happens immediately. You don't have to wait for it. And you have that power in most of the computers to do this. And then I'm going to do one more lecture, very short, just to give you an introduction to high performance computing as well. So we'll see how much